right now. Okay, so before I go into this exercise that's posted on Blackboard, I just want to discuss a little bit about this general principle. Okay, and this general principle that you learned about tonight is something called the central limit theorem. Okay, and we're going to learn what this really implies. Okay, let me just center this and get prepared really to kind of work on this a little bit. Okay, so here's a normal distribution. I'm going to just open this up so I can see if you're making any comments there. This is a normal distribution. Okay, I'm going to make up a population. I'm going to say the mean of this population. That's a parameter now. I'm using the Greek letter mu. So we know that that's a parameter. It represents the population. Mean of this population is 200. The standard deviation, I'm using sigma because standard deviation of the population, again, a parameter, is equal to, let's say, 20. Okay, now, if we were to look at this distribution of this population, the mean is in the middle. So it would have a z-score of 0, right, and be right about there. So the value 200 would be here. If we were to look one standard deviation to the left of the mean, this would be 180. This would be two standard deviations to the left, 160, 140, and to the right would be 220, 240, and 260, right? So we know from the empirical formula that 95% of the population, roughly, is between 160 and 240. Two standard deviations in either direction. 99.7% of the population is between 140 and 260, assuming it's a perfect normal distribution. 68% is between 180 and 220, and so on and so forth. And let's see, if this were 68%, this would be 34, and this would be 34. And from here to there is 50. So if this is 34, then the area above 220 would represent 16% of the population. 50 minus 34. And we have all sorts of other things that we can look at here that we can determine. Now, if we wanted to, let me see, undo. I just want to get some of this stuff out of the way. If we wanted to take a look at beyond the empirical formula at a value that's not a whole number of standard deviations, if we wanted to know what percentage of the population was below 216, that would be roughly around here, and the area would be what's to the left of that value. Well, we know the mean represents 50%, and had we gotten to 220, it would have been another 34%. So it would have been, 50 plus 34% would have been 92%. Would have been quite a bit of excuse me, 50 plus 34, 84%. So it would have been quite a bit of the entire population, but it didn't make it to 220. So it's more than 50%, but it's less than 84% because we didn't get that whole 34% here. So what would it be? We'd have to figure out a z-score for this value of 216. And the z-score is going to be the number of standard deviations above the mean, but it's going to be fractional, right? So z-score is equal to 216 minus 200 over the standard deviation, which is 20. Okay, that's mu minus x over sigma. Okay, or comes out to, what does it come out to? It comes out to 4 over 20. Excuse me, not 4 over 20, but 16 over 20, right? 16 over 20. 16 over 20 is 3/4 or 0.75. So the z-score is a positive 0.75. Well, I know I can go into my z-table. Okay, let me get things out of the way here. You see how easily I can do that. There we go. Okay, I want to get to my folder and to my z-table. Let's see. Let me go go back and find it again. I'll have to search. Here we go. Got my folder here. And my z-table from Agresti is here. I want to look up a value of plus 0.75. That'd be on this table. And I'm looking at the blue area, which is the area I was discussing. What percentage of the population is below that z-score? I'm looking, let's see. Let's see. I'm sorry, it's 0.8. 16 over 20 is 0.8. You're absolutely right. Okay, so I'm looking for 0.8. So 0.80 represents 70.81% of the population. So the area that I'm looking at is 0.7881 or 78.81% of the population is represented here. If I asked you what percentage of the population was above 216, it would have been 100 minus 78.81, right? Or 1.0 minus 0.7881, right? And it would have been, I guess, about 21%, a little over 21%, 0.2119, I guess, approximately. Okay, so that's what we would be looking at, right? Pretty straightforward. Except for the misstatement of this, it's actually, like, let me just correct that while I'm here. 0.80, right? 16 over 20. Okay, 15 over 20 would have been 0.75. Okay, so that gives us an idea of what we're looking at when we're dealing with a population. Well, we're going to give this a little bit of a twist now that we're talking about the central limit theorem. And let's take a look at what that's going to do for us. Okay, I'm going to take this, I'm going to leave that right there, and I'll work from here. Okay, so let's think about this. Same population, mu is equal to 200, sigma is equal to 20. And the mean is here, okay, which is 200. Okay, now let's say for a moment that we were going to take a sample of size 100 from this population. And we were going to find the mean of that sample of size 100. We're going to call that X bar instead of calling it X. Okay, well, we would expect that that mean is going to approximate the population mean. It's going to be if it's the same population where the average for everybody is 200, we'd expect if we took a big sample, like 100 is a pretty big sample, take a sample, it would also be around 200. Might not be exactly 200, right? Because we might get a few more people that are lower or higher on whatever score this is, but we'd expect it to be close to 200. And we would, if it were less or more, we would expect it that it wouldn't. It's less and less likely that it'd be very far below or very far above 200, especially with that big a sample size. Well, let's think about this for a second. What's going to happen here is that when I take repeat, if I were going to look at all of the samples, if I took a sample of size 100 from this population, well, maybe I get lucky and I find the mean equal to 200. I do it again, and this time I get a mean equal to 205. I do it again, this time I get a mean equal to 198. I do it again, I get a mean equal to 201. I do it again, you get a mean equal to 197. I do it again, I get maybe a 200 again. Do it again, maybe I get a 199. Basically, what's happening here is that when I take a large sample from a population, the variability of the means that I get taking a large sample over and over again from the same population, the variability that I get is much smaller than the variability in the population. So now instead of, remember this was mu equals 200, sigma equals 20. If this represented the population, then I would have 95% of the distribution would have been between 160 and 240, right? Two standard deviations on either side would represent 95% of the people in the population. Well, now when I take a sample randomly, I'm going to get samples of some people that are higher and lower, all these different individuals. When I take that average, well, that average for a sample size of 100 is going to be much closer to 200 than most of these individual values are, right? So if I do it over and over again and I plot a new distribution, that's a distribution that represents all of the repeated samples that I would take of size 100. And now I plot a new distribution that represents all of those values. That would be normally distributed also. And the mean of this new distribution would approximate the same mean as the population. The only difference is that it would be a much narrower distribution. You wouldn't expect to get 20 people, 100 people all at the tail end of this and get a very low average. That's going to be a much narrower distribution. There is, in fact, a mathematical relationship here. Actually, this new normal distribution that's based on repeated samples of size 100 from this population now has its own standard deviation. And that standard deviation is going to be equal to sigma, the standard deviation of the population, divided by the square root of the sample size. So what does that tell you? That tells you not only, since you're taking sigma and dividing it by a whole number, that tells you that the standard deviation of these repeated sample results is going to be much smaller than the standard deviation of sigma, but also it tells you that the bigger the sample size is, the smaller this standard deviation is, right? So if I had taken a sample size of only 10, well, it would have been narrower than normal population, but it wouldn't have been quite as narrow as this larger sample size of 100. Okay, so this is our new distribution for samples, repeated samples of a size n from a population that's normally distributed. I'm going to get to that later on because we can actually cheat on that a bit. And maybe the population, the original population, doesn't have to be perfectly normally distributed. Okay, so first time out, I would expect that is probably clear as mud, right? Am I wrong about that? Give me some feedback. How do you guys feel about that? Does that make sense to you, or is it as I suspect as clear as mud? Let me get a little bit of feedback on that second. Okay, I got one good. One person I didn't lose yet, right? Okay. Not yeah, it's not super intuitive, is it? It's a really important concept. Okay. The reason why it's a really important concept is because we often I'm going to get I'm going to get a new version of this now that we can look at. And okay, the reason why it's a really important concept is because we never know the population. Okay, that's very rare that we would know what mu is. Most of the time, we have no clue what mu is. Often we don't know what sigma is. For the moment, we're gonna, like make believe that we know sigma for a lot of these examples because it's important to know sigma because that's how we figure out what the standard deviation is that we're gonna have to work with. Okay, so for the moment, we're gonna take a little latitude and make believe that we do know what the standard deviation of the population is, but we almost never know sigma. When we take a sample from a group or a population of some kind, what we're after is estimating mu. What is mu equal to? What's the population mean equal to? Well, when we take that sample, we don't know what the population mean is equal to. All we know is the mean of the sample that we took. Okay, so now if we know the mean of the sample that we took, we're interested in knowing how that behaves relative to the mean of the population. Okay, so this opens up some opportunities for us. Okay, let's see. Let me just take a quick look at the questions here. Is sample distribution more narrow because small you get more likely to get values than yeah, Margaret, I think you got the right idea. You're not very likely to get all values on one end or all values at the other end. You're likely to get either a scattering of them all over the place, so the means So when you take an average of all those values that you've taken randomly, they're closer to the mean than most of the any of the individual values are likely to be. Okay, so I see another request to explain it one more time. I'm going to do it again. I'm going to do something first, but I'm going to do it again, looking at it another way. And somebody jumped the gun and beat me to the punch here. Thank you, Jennifer. That new standard deviation, that new standard deviation for sample means, if you repeatedly took samples over and over again, instead of calling that the standard deviation, we assign that a new name to so we don't confuse it with the standard deviation of the population or even the standard deviation of the numbers that were within the sample. We call that the standard error. Okay, so that's what we call the standard error, or you could call it SE. Okay, so now let's take a look at something interesting about this. Let's say I told you that that the mean of this population was 200, as I told you before, right? Mean is 200, and the standard deviation sigma is equal to 20. Okay, well, let's say I said I'm going to take sample size 100. The standard error is going to be equal to sigma. Remember, that's the standard deviation of the repeated samples of size 100 over and over again, and then redrawn as a distribution. And that's what this distribution is going to represent now. Standard error is equal to sigma over the square root of n, which is equal to 20 over the square root of 100, which is equal to, that's 10 divided into 20 is equal to 2. So now the standard error is equal to 2. So the mean of all of the samples that we would take from this population, assuming we sampled over and over again, the average result would be 200. Sometimes we get under 200, sometimes we get over 200, sometimes we get lucky and get exactly 200. But now the spread here has changed tremendously. The standard error is equal to now our which is the standard deviation of these repeated sample values. The standard error now is equal to 2. So one standard deviation below this would be 198. 2 would be 196. And this would be 202. And this would be 204. Well, what does that mean? That means that if we took from this population, if we took a sample of 100 people, right? Took a sample of 100 people, right? If we did that, 95% of the time we would get a result between 196 and 204. 95% of the time, the mean that we got for those 100 randomly selected people would have been between 196 and 204. Two standard errors below the mean and two standard errors above the mean. Okay, how does that contrast with if I go back and look at the actual population, right? Well, if I looked at the actual population and I took a random individual, 95% of the time he would be between 160 and 240, a much bigger spread than if I were to take a sample size of 100. Then 95% of the time we would get a result for the mean that would be between 196 and 204. And this is going to hold up in a lot of situations, even when things are not perfectly normally distributed. Okay, and why is this important to us? The reason why this is important to us is because we never know the real population. It's very rare for us to know all of the values for the entire population and be able to make big predictions based on that, despite all of the examples that we had before where I gave you that the population mean is such and such. And so remember, up until this point, we haven't mentioned sample means at all. We've always been dealing with population means and population standard deviations. Okay, but now we're dealing with sample means. Okay, so now let's take a look at this. Now we have a mechanism for understanding how likely it is for us to get values that are within a certain range based on the standard deviation. standard error rather. Okay, so now let's take another look at this another way. I am going to go back to this exercise that we have. Okay, here's the exercise that we have. Oh, that's actually the Excel version of it. I think it's behind here. Is that it? Nope, that's the Z table. Let me find that Word document if I can find it, or I'll just reopen it. Okay, here it is. Okay, I'm going to take a look at this example. This is 100 numbers. These numbers happen to be normally distributed. Yeah, this will be available for download. This will be this is I can understand you being a little lost if you just tuned in, but don't worry about it. You will be able to download it. And in fact, I'm going to go over the principle that we just discussed. In a sense, I'm going over it now again from a new perspective. Okay, so this document that I have here, and I'm going to leave it up in a little bit. You can actually you're going to be able to help me out with something here. This is an entire, these numbers in here are numbers that represent, I don't know, it could be ages or something like that. It could be anything, right? These numbers are normally distributed, okay? And I'll tell you, let's take a look. I wonder what the mean of these numbers is. Let's see what the average of these numbers, okay? And I actually have a version of this in Excel, okay? Same table, okay? I'm going to find the average here. It's going to be equal to average. Let me see if I can't get this so I can see it. Average, percentage, okay. And let's see, the average of all of these numbers is going to be 50. The average of all these numbers is 50. The standard deviation for all of these numbers is going to be, and I'm going to do this again, B2, whoops, B2 through, what is that? I can't see it there. K, whatever it is, K13. Okay, I think I might have missed it there. Let me try that again. Let me reduce the size of this so I can actually see it, and I'll blow it up again so you guys can work on it. Equal, standard, deviation, parentheses, and I'm going to highlight from B2 through K11. That's easier for me to do now. So the mean of this population is 50. The standard deviation of the population is 9. Okay, that's because we included everybody here. Okay, so now I'm going to ask you to help me out. We're going to take repeated samples from this population. I'm randomly going to select people in this population of 100 people. I'm randomly going to select people, and I'm going to select 9 people from this population and find the average for those 9 people. So we're going to take a sample size. That's going to be equal to 9. So now we're going to go here and take a random sample. Now, one of the ways I could take a random sample is I could just, blindly click in here, put my finger and click, click, click. Problem with that is that we're going to have biases. You might be right-handed, you pick more people on the right. You're left-handed, you might pick more people on the left. So we need a way to pick a truly random sample from this population. Well, it happens in Blackboard. One of the files I posted was, okay, where is it? Let me find it. Getting crowded here. I need a bigger monitor here or something. Here we go. Random number table. This is actually from the back of a Gretzky. If you happen to have the, okay, don't need the Z table. I need the random number table. Let's open random number table. See if it opens for me. Must be closed down here. Let's see, normal distribution is in the random number table. Okay, so this random number table has been prepared. It's been done mathematically. It's been prepared. These are random digits. Got 3 ones in a row right off here to start, but that's just by coincidence, by chance. Okay, so 1 1 1 6 4 3 6 3 1 8 7 5 so on and so forth. Or the sequence of these numbers has been created in a random manner. So what I'm going to do is, if you notice, I made this table, I set this table up so that it has 10 rows and 10 columns. Okay, so if a number, I'm going to use the rows, the columns is the first digit, and the rows is the second digit. So if I were to pick a random spot to start here, I'm going to start here. The first number I come across is 14. So 14 would represent the row 1 and column 4, which would be number 54. I'm going to write that down. Okay, so the next number I come across is 06. So that would be 0, 6 would be 58. Okay, so I'm going to pick 9 numbers based on this random number table. The next number would be 39. Okay, see, I'm going right across the row there, 39. Third row, ninth column would be 64. The next one would be 31 and then 04. 31 would be 49 and 04 would be 04 would be 58. And the next one would be 78 and 48. 7, 8 would be 45. And what was the other one? What was the next one? 78 and 48. 4, 8 would be 6, 9. Okay, and how many I got here? I got 4, 5, 6, 7. I need 2 more. 48. Then next there's going to be 37 and 27. 3, 7, which is 54. And did I say 27 after that? 37 and 27. 2, 7 is 39. Okay, so now I'm going to take, this is my sample. It's as if I didn't see these numbers. I took them randomly. So I'm going to find the average for my sample. The average for my sample is 54. It's higher than the population mean, as it happens in my sample. Now, what I'm going to do now is I'm going to ask each of you to do exactly the same thing. Grab the random number table. It doesn't have to be the first page. Just click in somewhere and start. Like, yeah, I might have started at 99. Right? Click in somewhere. I might have started at 33. Click in anywhere on that random number table and use that to get 9 numbers randomly from this population of 100 and find the average for those 9 numbers so that you and I will assemble a sample of repeated samples of size 9 from this population so we can see how it behaves. Okay, so I'll give you a few minutes to do that. And as you do it, as you get that done, I want you to type in the number into the chat box so I can see what number you got. I can't play music while we're doing this, and I could, I suppose, but it comes out really funky. Like quiz music, like the $64,000 question or something like that, or Jeopardy. Okay, there's no right or wrong answer here. You're just going to randomly select 9 numbers, using that random number table from this population, and just echo them back in the chat box. Okay, got my first entry was a 65. Boy, that's pretty high. Okay, next. Whoops, I'm handling the. I have two input devices here, so it jumps around every once in a while. Next, I got a 36. Okay, remember I want the average for the 9 values. And if you want to do it more than once, you're perfectly willing to, because I need a number of values to evaluate to figure this thing out. $48, good. Looking good so far. $51, thank you. Okay, let's see, I got a 52 and a 47. Okay, just could use a couple more. I got a 46. Any other volunteers there? Maybe one or two more numbers if I can get somebody to give them to me. Oh, I got a 58 and another 46 and a 45. 58, another 46, and a 45. Okay, I think that's enough. I think that's enough. Now, I'll tell you, I'm going to eliminate one of these numbers. I'm going to eliminate this 65 because I'm looking at these numbers here. And boy, you have to, if you're going to choose 9 numbers, there's barely 9 numbers that are really that high. So I'm going to ditch that one. I'm going to call that outlier and ditch that one for my own purposes. Just trust me for the moment. I know I'm being bad, but what can I tell you? Okay, so I'm going to take this. These are the results of averages for each of the individuals. Each of you people took an average of 9 individuals randomly selected from this population. These are the means that you got. I'm going to find the average for all of these values. So I'm going to say, let's see what that's going to be. Let's see what that's going to be equal to. Well, the average of all of these values, all of these means, is 48. That's not too far from 50, is it? Right? The population mean was 50. So 48, it's kind of close. Now, even more, except this would be the mean of repeated samples, right? Sample means. Okay. Now I'm going to take the standard deviation for repeated sample means, or what we would call the standard error. Okay, and that's going to be equal to STDEV parentheses. And I'm going to highlight all of these numbers, and that's within that range. And the standard deviation is 6. Let's go back and look at the population. The mean was 50, and the standard deviation is 9. Well, what did we get for the, if we look at the individual values we got, well, we got a value for 9, for sample size of 9 that was 35. We got one as high as 58, and so on and so forth. So there was quite a spread on it. But when we looked at the average overall, we got very close to an average of 48. We also found a standard deviation of 6. Well, now, remember the rule I gave you before? We know that the standard deviation or standard error, I'm going to change that right now. I'm going to change that to an E. The standard error for repeated samples of size 9 is going to be smaller than the standard deviation for the population because the numbers are going to be closer together than the people in the population because we're averaging them. Yeah, I'm trying to make it work out. Okay, I'll take 36 out. I'll tell you what, I'll take 36 out also. Okay, see what happens if I take 36 out. Well, we wound up with a mean of exactly 60 and a standard deviation of 4, standard error of 4, if I did that. Okay, so the comment that brought that up, let's say you got to take 65 out. Why don't you take 36 out also? Well, I did, and as a matter of fact, look at this. I got a pretty interesting result. I got a mean exactly the same as the population, and I got a standard error of 4. Well, now no, we're not. No, I'm just doing this because I want this example to come out reasonably well. And I was hoping to get 25 people giving me numbers, but I didn't get enough people giving me numbers to get a really good handle on this. So, yeah, if I added them both in, I have a problem with that, though. It's going to make my standard error blow up. I'm not sure how I wound up with those numbers so far apart, so far out, because there's so few values that are 39. I'm guessing that maybe there might have been an error or something like that somewhere, involved there or something like that. That's a possibility, but who knows? But at any rate, I'm not concerned about that. I just want to use this as an example. Now, if I told you, based on that rule that I gave you before, called the the rule that we discussed, where we're going to base the value of the standard deviation of central limit theorem. Thank you. Yeah, I'm having a long day here. The central limit theorem, that rule that I gave you, the central limit theorem, one of the things that I said was that if you took repeated samples, many, many samples from a population, the average for your repeated samples is going to approximate the population average, right? And did it? It actually did that, didn't it? It approximated the population average, right? Thank you. And I also told you, that the standard error is going to be equal to the standard deviation of the population, sigma, divided by the square root of the sample size, square root of n. Okay, well, sigma is 9. If we're going to divide that by the square root of the sample size was 9, square root of 9 is 3. So 9 divided by 3, we would have predicted that the standard error was going to be equal to 3, is what we would have predicted. Okay, in fact, what we found was the standard error for the one that we actually did. Remember, we only did so many numbers here. Standard error was 4, pretty close to that 3. But we can kind of at least see that this mechanism really works. It has some validity. That if we take repeated samples from this population, we can predict that if we make a new distribution from those averages for those repeated samples from this population, whatever size they happen to be, when we make a new distribution, the mean of the distribution of the repeated samples is going to approximate the population mean, and the standard deviation for this new distribution is going to be equal to the standard deviation of the population divided by the square root of the sample size. The bigger the sample size is, the smaller the standard error, or the tighter that this new distribution is going to be. Okay, is everybody at this stage at least a little reasonably comfortable about this? Give me a yes on that. Okay. All right. I'm kind of like hammering this away at this because this is a really important kind of concept on what we're going to proceed on as we go forward, because from now on, when we deal with real statistics, we're gonna be dealing with samples, not with the populations themselves. But we're going to use those samples to improve our understanding of the population. So let's go back to what we had over here. I'm gonna close this. I don't think I need it anymore for now. I don't think I need my random number table anymore. So I'm gonna go back to my Word document over here. And okay, we kind of did what we did here. Now, the next exercise I'm going to do here involves the normal distribution, the z-table, and maybe if we get lucky, we might be able to do some stuff with the empirical formula. Okay, so normally distributed with a mean of 200. Okay, this is this is, I don't know what this is, blood sugars maybe or something like that per 100 deciliters, I guess, or per 100 milliliters. Um, uh, 200 milligrams per 100 milliliters, and a standard deviation of 20, cholesterol, 20 milligrams per 100, exactly the same thing I was just discussing. Okay, find the probability that an individual picked at random from this population will have a cholesterol value between 180 and 220. Okay, I can see just by looking at that 180 is one standard deviation, 20, below the mean, and 220 is 100 is one standard deviation above the mean. So what's the probability they'll have a cholesterol value between these two values? I'm guessing that you guys don't even have to draw that. You guys would probably know that. Oh, one standard deviation, not two, right? 68%, right? You all agree on that? Right? It's not 95, it's 60, 68 because it's one standard deviation. How about between 160 and 240? What percentage of the population would have a value between those two? Well, now we're talking two standard deviations below and two standard deviations above. So that would be 95% now. Excellent. Great, Jennifer. Okay, what's the probability that we would have a cholesterol value? We pick an individual from this population, and he would have a cholesterol value bigger than 225. Another way to state this, what percentage of the population has a cholesterol value that bigger than 225? Same idea, right? If 10% of the population is above that, then the chances of my randomly picking that person is 10%. So you really really the same way as stating the problem, but we got to be above 225. The problem here is that now, it's not an even empirical formula type z-score, because it's not exactly one or two or three standard deviations. So now I think it'd be a good time to go to my notebook and draw this out. Okay, that's ugly. Let me change that. Okay, here, let me put this distribution in here. Okay, so remember, dealing with the population now. Okay, mean is, 220, 200 rather. Standard deviation is 20, and we're dealing with 225. Okay, so we want to know what's the probability of being above 225. That's what the question asked us, right? So let's see, 225, what's the z-score for 225? Well, z is equal to x minus the mean over the standard deviation is equal to 225 minus 200 over 20. 25 over 20 is going to be equal to 1.25. Go to our z-table. Okay, if I can find them. Okay, z-table. And let me see if I can't get to it here. Here's the z-tables. So z-score of plus 1.25. 1.2012345 would be 0.8944. Okay, so if I go here, this area to the right, remember we always go to the right, is 0.8944. That's not what we asked. We asked what percentage of the population, or what's the probability of picking an individual that's above 225. As it happens, the z-table only gives us the area below here. So it would be 1 minus 0.8944, and that would be 6. Okay, let's see, 6, carry the 1 from here, 5, carry the 1, do I got this right? 0, 9, 1, is it 10.056? I think it is. I think that's right. Okay, 0.1056, right? So this area would be 0.1056. If I expressed it as a percentage, it would be 10.56. One caveat here,
If I ask you on the test to express it as a percentage, please give it to me as a percentage. If I express it, suggest you express it as a probability or p-value, then put down 0.1056. I'm not going to mark you wrong if you do it the other way because they're really equivalent, right? But some of the short answers and stuff like that. On when we use a Blackboard to do the exams, they'll auto grade, and it's easy for me to miss it if it grades you wrong. Because you gave the answer in the wrong format that it wasn't asked for. I always go back and kind of check those. But I don't want it to slip past me. So try if you can. I'm not gonna mark it wrong, but go back and see if you can't. I'm sorry. See if you can't read the question carefully and respond as it asks. I'll try and always put in some sort of direction as to how I want the answer phrased. Okay, so we're still dealing with a normal population. Okay, now less than 150 milligrams. Well, we do the same thing. We'd calculate a z-score for 150 to be a negative number, and we're looking for people smaller than that, so we wouldn't have to subtract one. Between 190 and 210. Well, a couple of ways for us to do that. We might find the area below 190, and we might find the area below 210. And since the area below 190, if we subtract that from the area below 210, it'll leave us with the area between the two of these. Okay, so it's pretty basic stuff. It's stuff we've been doing all along. Okay, so now let's take a look if we push this just a little bit further and apply the central limit theorem. We take a sample of size 25 from this population that we're working with above. What's the probability that the mean of the sample that let me undo that, that the mean of the sample that we just took of size 25, the mean of that sample of size 25 from that population, what's the probability that that mean is larger than 204? Okay, I'm going to give you a second to think about that. You can volunteer an answer if you want. I'll give you a minute to think about it, and then I'm going to work it out over here. Okay, just so you can get a shot at it, right? I don't expect most of you to really get this right off the top right away, but just so you can get a shot at it and see who the first person to come up with a possible answer is. Who's going to stick their neck out? Anybody? I don't want to keep you guys waiting too long, so I'm not gonna wait on an answer if I don't get something in a few seconds. Oh, standard error. Okay, standard error is 4. That's a good start. Well, let's see what standard error is. Okay, actually, I'm looking for. Remember, we're looking for the probability of getting a mean for that sample size 25 larger than 204. Okay, so now we know as it happens, we know the mean is 200. And we also know, the mean, mu, is 200. Sigma, the standard deviation, is 20 for the population. So now we would expect that the mean for repeated samples of size 25, now we're going to deal with the samples. Distribution, now this is going to represent the distribution of these sample means for sample size equals 25. Oh, I got one response here. We're going to check that and see if it's right. Okay, Gerald, hang on a second. For a sample size equals 25. Well, we know that if we take enough samples repeatedly of this population, we get the same mean eventually as the population, 200. But now, instead of using the standard deviation of the population, we're going to use the standard error, which is going to be equal to the standard deviation of the population, 20, divided by the square root of the sample size, which is 20, divided by the square root of 25, which is 5, which is equal to 4. So bingo, person that just gave me the standard deviation, that was Michelle, she's right. Okay, now let's figure out what percentage of the population is going to be. So now 200. So let's see, standard deviation. This is now kind of our standard deviation. We call it standard error because it represents distribution of samples. But let's see, this is going to be 204, 208, two standard errors, 196, 192. Okay, so two standard let's see, 204 is going to be here. It's going to be one standard deviation above the mean. So what percentage is above that level? Well, I can even use the empirical formula here. Okay, one standard deviation above, one standard deviation below would be 68%. Means between the mean and here is 34% because the normal distribution is symmetrical. Okay, and that would leave in here roughly 16% of the population. So 16% of the samples would be greater than 204. Okay, so not 32, 16, right? Do we see why it's 16? Because I'm asking for the percentage that's above one standard deviation, just like before. Okay, yeah, right, two-tailed. Okay, everybody at least reasonably comfortable with that. I'm doing the same thing I was doing before, except now I'm dealing with a sample distribution. And the only thing that really changed here was that we're using the standard error instead of the standard deviation. Okay, let me see if we have another question from that group. Okay, what's the probability that, okay, what's the probability that the mean of the sample is between 192 and 204? Okay, it's a probability that sample that we took would be between 192 and 204. Well, let's see what 192 is. 192 is two standard deviations to the right of the mean, to the left of the mean. 204 is one standard deviation to the right of the mean. So this looks very interesting. Okay, I know that this port, if we had two standard deviations, there's a lot of ways to skin a cat here. I'm looking for this area between these two values, right? So there's a few ways that I could do this. One way that I could do this is I could say to myself, well, this I know is 34% right here. Now I know everything from the mean down represents 50%. And since I know that two standard deviations away from the mean is part of that 95%, remember we said 95%, that would leave 5% that's outside of that area, which means in this tail, only 2.5% is outside of it. The other tail, the other 2.5% would have been outside of it. So this area in here has to be 47.5%. So if I'm looking for the area between here and here, added to the area here, I'm going to add 47.5% to 34%. This isn't the only method that I can use to do this. Okay, do you see how I got that? Right? Okay, roughly, is that what it comes out to? About 81%? 34? Yeah, about 81.5% actually. Okay, so I'm not sure how you end up with 74% using the empirical rule, but uh, uh, but it's I know it's a little bit confusing, especially if you haven't had a lot of practice with it. But if you kind of keep this stuff straight, you can there are many other ways that you could kind of muscle out like what these areas are. Okay. Got to look at the wrong. As long as you understand where the mistake was, that's really the important part at this stage, anyway. Eventually we want to get it right. Right now, we just want to understand it. But the long term goal is to actually get it right. Right. Okay. So now let's take a look at one more question here that deals with the same thing. A sample of size 100 is taken from the population above. We're doing the same thing, except sample size now, n is going to be larger. Within what range would we expect 95% of the samples to fall? Okay, first do it using the empirical rule and then use the z-table. Okay, you want to know what range would 95% of the samples fall. I'm going to go to this next page. Okay, again, Okay, so this time, let's see, X bar, right? So the mean that we expect here is going to be 200 if we take repeated samples. Standard error is going to be equal to sigma over the square root of the sample size, which is going to be was 20 divided by sample size now is 100. It's going to be divided by 10, so that's going to be equal to standard error is going to be equal to 2. So one standard deviation is going to be 2 plus 200 is the mean, 202, 204. This is 198, 196. Thank you very much. That's right. Okay, 196, right? So it's going to be between here and here, right? So the answer would be that 95% of the sample means would be between 196 and 204. Okay, that's the range that we would expect them in. So now, I've also asked, the problem also asks, well, instead of using the empirical formula, use the z-table. Interesting thing here now is the z-table is going to give us an exact result. The empirical formula is only an estimate. So let's go ahead and do that. I'm going to start with this point right here, the 204, 2 standard deviations above. US beat Ghana in the World Cup. Just got a little text message on my phone there. So it's still going to be tough for them to get out of that group before that they're in. But hopefully maybe they pull out another good game. So at any rate, so we're going to use the z-score here for a z-score of 2. Okay, I'm going to look up what the area is in this distribution for these sample means from here down. Okay, that whole area. It's going to be more than 95. We know from here to here, right? From here to here is 95%. So this is going to be more than 95% because it includes this, right? So let's go take a look at our z-table. Let's see where the z-table is here, where that hid now. Okay, let me do it this way. Okay, here's our z-table. Okay, so z-score of 2.00 is 9792. Okay, now go back here. So this area from here down is 97. Did I say 92 or 72? 9772. 0.9772, 97.72%, right? So that's the total area from here down. Well, we don't want the total area from here down. We only want the area from here to here. So now what I'm going to do is I'm going to go to my z-table and look up the z-score, look up the area below -2, right? So let's go look that up. So -2 is going to be back here, -2.0 is going to represent an area, -2.0 of 0.22028. That area is going to be 0.0228. So the area between -2 and +2 z-score using the z-table is going to be 97.72% minus 2.28%. We're going to take this entire area and then subtract this from it, leaving just the area that we want. Let me do that, 0.9772 and 0.0228. Okay, it's going to be 6, carried 1, it's going to be 4, 4, 5, oh, it's going to be, excuse me, 9, wow, 0.95. So this area between these two is going to be 95.44%, or as a decimal point, or probability is going to be 0.9544. A bit more than the 95% that the estimate that the empirical formula gets us, but this is more exact.